You should have a periodic table to color in already. This one's a little dated. The last few elements that you see on the screen here have been named already, and we have names for 114, 116 already as well. But it took a lot to make this presentation, and I've not updated the periodic table in the background. You should be able to see why here in just a moment. So a couple things to point out or highlight before we move on with naming the groups or families on the periodic table. First off, group is another word for family. Although technically speaking, group is columns only, and some of the families do go over more than one column. But group or family I'll use interchangeably to refer to the columns or groups of columns on the periodic table. And we talked previously about Mendeleev's periodic table, how he had some columns mixed in together, and later on we realized that those probably should be separated apart, and so that led to a naming system. He originally called them Roman numerals 1 through 8, and so we ended up calling them Roman numerals 1 through 8A and B, although how the Europeans did it versus how the Americans did it were different, and so we had different naming systems, and finally the International Union of Pure and Applied Chemistry that's in charge of these things said, let's just renumber them 1 through 18. So make that change on your periodic table. While you do that, I should point out that down here on the bottom two rows, those are not actually, don't actually belong to, but instead lutetium, lawrencium go underneath scandium, yttrium, and the other 14 go right here in between barium, radium, and lutetium, lawrencium. And so really the periodic table should look like this slide here, where I have the extended form or long form version of the periodic table. Lutetium, lawrencium underneath scandium, yttrium, and those 14 down there. And so really there's 32 columns in the periodic table. Fortunately, those bottom two rows, they kind of behave similarly by row instead of by column. There are similarities by column still, but for the most part they behave similarly by row, and so we put them underneath and we ignore them on the numbering system with the 1 through 18. But they would be between 2 and 3, except for the last two here, which are in column 3. Anyway, periodic table is really the periodic table of the elements. It's the elements that are in periods, and periods is a fancy word for rows here on the periodic table, but even more than that, periods refer to things that repeat regularly. And so periodical is some kind of publication that gets sent out on a regular basis, whether it be a daily newspaper or a weekly or monthly magazine, sometimes even quarterly magazines. Those things are called periodicals, or things that come regularly. Anything that comes regularly is considered to be periodical in nature. And the reason periodic table of elements is called that is because there are patterns, and it's those patterns that Mendeleev used, others used as well before him, but to try to organize them into where the patterns make sense. Anyway, there's a stair-step line that you should draw in. It goes down along the side of boron over here, and then it goes over, down, down, over, and all these overs are to the right, down, right, right, down. Again, down, right, down, right, down, right, right, down. And that stair-step line is what separates the metals on the left-hand side from the non-metals and other things on the right-hand side. In this presentation, I'm going to put almost everything right up here in the middle. However, I would recommend you right here, real tiny, write metals that way, non-metals that way, just because it's going to be a good dividing point. And if you write everything here, it's going to get way too crowded. Anyway, that's not even a perfect division. There's some debate about exactly where that stair-step line goes, but that's what we'll use. And then, what I recommend is that you flip to the back of your periodic table and just jot down these notes here as we go. If you run out of room, jot them in your notebook or somewhere else. Anyway, some quick facts about metals. Metals are shiny, and that may sound silly, but that's actually an important property. It has to do with their electrons and how their electrons are on the outer surface and able to reflect photons back to our eyes. But metals are shiny. The other things are not. Metals are good conductors of heat and electricity. Some metals, not all metals, are magnetic. It's very wrong to say that all metals are magnetic. Aluminum and copper are the two you come across most often that are not magnetic. But they're all good conductors of heat and electricity. They are malleable. That means they can be beaten into different shapes. And ductile, which means they can be pulled into long wires. If you've ever looked at the filament in a light bulb, it's a really, really tiny wire, and they get that by taking a cylinder of tungsten and just pushing it through with with a mechanical press through a really tiny hole and getting the wire out on the other end. Those two together could be combined to say that metals are flexible. I should point out here, most metals are solids. It didn't make the list, but most metals are solids. There's one exception to that. There's also one non-solid, one liquid on the right-hand side of the periodic table. For the metals, it's mercury. Metals tend to give away their electrons, and because they give away their electrons, they're getting rid of negative charge, and that means they end up with a positive charge, and they form positive ions. Ions, if we've not mentioned it already, are just the fancy word for charged atoms. Anyway, what we're going to do from here on out is we're going to color one group at a time, the groups on the periodic table. Not one element at a time, but hydrogen here happens to be the first one. By the way, if you have a least favorite color, I recommend starting out with this one because it is our smallest group. If you want to follow my pattern, I'm going for a rainbow color here as I do this one. If you have a favorite color, save it. I'll tell you when to use it here in a bit. Anyway, hydrogen belongs to the hydrogen group, and what we'll do for each of these is we'll jump to a slide about the group then. So shade in hydrogen real quick, and then notes about the hydrogen group. Hydrogen is an element that is so unique, it's in a group all by itself. It can bond to itself, which means when you find it in nature, you never find it alone. You always find it bonded to something else or bonded to itself. If it's bonded to itself, the formula is H2, two hydrogens bonded to each other. It has one valence electron, and kind of unique among the elements, it can give it away or it can gain just one, which means it can form one plus or minus ions. By the way, there's no difference between plus or minus 1 and 1 plus or minus. Most chemists that I've come across in most textbooks tend to write the number then the charge, which is how I tend to do it, as that's what I was taught. If you write it different, I will not penalize you. Also, just so you know, usually when the charge is just a 1, we usually don't write the 1, we just write a plus or minus, and if it is something other than 1, then we'll write the number in there. Back to the front, we're going to do our next group. The rest of the column that hydrogen is in, that group is called the alkali metals. A-L-K-A-L-I, alkali metals. And some notes about the alkali metals. First off, they are soft, and so frequently when I ask for properties of metals, people say hard, and I'm like, not all metals. Alkali metals happen to be soft. They are very reactive elements, some of the most reactive on the periodic table. And that's because they have one valence electron, one electron on their outermost energy level. You've seen this when we've done electron configurations. They all ended -1. They have one electron on their outermost energy level. They tend to give that one electron away, and that means they end up forming a 1 plus ion. Our next group is right next to that column. It's the whole column, and those are the alkaline earth metals. A-L-K-A-L-I-N-E, earth metals. I wish I was in charge of naming these things. I would have named them something different. I'm not. I apologize. You do need to know the difference between the two. I'll try to point out real quick here. The way I remembered it is that alkali metals and alkaline earth metals, if we drop the word metals from both of them, alkali is 1 word long, alkaline earth is 2 words long, and they're in the second column. Also, alkaline earth has a longer name. It's alkali versus alkaline with the NE at the end. And so the longer word, the 2 words together, second column. It's not a great help, but it's how I've been able to tell them apart for years. Anyway, flip over to the back. Couple notes about them. They are reactive, not as reactive as the alkali metals, but they are reactive elements. They have 2 valence electrons, and they tend to give them away to form 2 plus ions. So, back to the front again. Now it's favorite color time. We have the big middle section, the indented section here, as I usually call it. That group, as well as the ones underneath that really belong there. Those are all called the transition metals. This will take you a little while to color. Go ahead and pause the video, and when you're ready to move on, resume. Anyway, so notes about the transition metals. These are the metals that are hard. These are the metals that we think of when we think of metals. When I think of metals, I think of copper, I think of iron. Those are the ones that stand out, and they are hard metals. As a side note, I also think of aluminum and lead. Those belong to the next group over. We'll get to them here in just a moment. But the transition metals are all hard metals. There is an exception there. Mercury happens to be in the transition metals, and it's the only one that's a liquid at room temperature. When it's frozen, it's hard, but that is is when it's solid, it's hard, but you have to freeze it to do so, and you actually have to go pretty cold to do that. Anyway, they have a various number of valence electrons, and because of that, they form various positive ions. In fact, most of the transition metals can form more than one ion. Iron can form a +2 and a +3. Copper can form a +1 and a +2. And so most of the metals here can form more than one ion, so there's no real pattern to list on that right now. Those patterns will become important here soon, though. Back to the front, and our next group is everything up to the stair-step line, and that group is called the other metals. Recently, I heard a name for them. They are called the poor metals as well, another name for them. We just didn't have a good name for them, but having said that, there's quite a few very common metals in here. Aluminum is there, Sn is tin, lead is Pb, my favorite element, bismuth, Bi is there. Great group of metals, but the first of our radioactive metals, polonium is there. Just an interesting mixed group. But it really is a mixed group. And I don't have any special notes over the other metals. I mean, they form positive ions still, like most metals, even though they begin to get into the side of the periodic table where most things are getting negative. No special notes over them. So now everything right next to the stair-step line, everything else that's touching the stair-step line except for astatine here, I suppose you could say iodine's on the diagonal there, so nothing in either of those two. And add in, I guess skip carbon as well. But everything that's touching the stair-step line otherwise, except for if they're in the next to last column. Anyway, it's just 6 elements. Boron, silicon, germanium, As, which is arsenic, Sb, antimony, and tellurium. Those really, sometimes the stair-step line I mentioned earlier is drawn over here because that group is the metalloids. We're still not totally away from the metals here. The metalloids are also known as semimetals or semiconductors. Semiconductors is really their use, but semimetals is another common name for them. But they have both properties of metals and non-metals. They can sometimes conduct electricity, heat, and magnetism. That's it. As far as their properties, look at your properties of metals, or what we'll get to here in just a moment, their properties of non-metals. So our next group to color in is everything except for the very last column. And this group, as I've referred to a few times, is the non-metals. Technically speaking, we probably could consider the last column to be non-metals, but the last 2 columns here are the only columns where the whole column is the same thing. And because of that, both of those have special names, which we'll get to here in a moment. But really, this last column here, they could also be considered non-metals. Some people won't include this column here just because it does have another name. I'm going to go ahead and label it as both, as you'll see here in a moment. So non-metals are pretty much the opposite of metals. So if we go back to our properties of metals, metals are shiny. Non-metals are dull or earthy. Metals are good conductors of heat and electricity. Non-metals are poor conductors, which also means they're good insulators of heat and electricity. Metals are flexible, they're ductile and malleable. Non-metals are brittle. I did mention in there, by the way, metals tend to be solid. Non-metals can be solid or gas, and there's one liquid on the non-metal side as well. We'll label it here in a bit. Metals tend to give away their electrons, non-metals tend to gain their electrons. And because of that, non-metals tend to form negative ions. Because they're gaining extra electrons, the electrons have a negative charge, so if you get extra electrons, you end up with a negative charge. Before we get to the last column, the next to last column, because that group is all one thing, it's our only non-metal column where everything in the column is the same thing. All our others have some metalloids and some other metals in there. Because that group is there, it has a special name. These others have special names as well, but they're not worth learning. Anyway, group 17 there, that is the halogens. You've possibly heard the name halogens with light bulbs, and specifically halogen lamps or lights tend to be used on cars for headlights, really bright ones, although there are also some krypton xenon ones out there as well. Anyway, the halogens are mostly gases. Having said that, there's actually 2 that are not, and we don't know on astatine. So really, it's fluorine, chlorine are gases, but the 2 that are not. Bromine is our only liquid non-metal, and if you go to equatorial regions, it's hot enough most of the time that it's a gas instead. And iodine, you don't have to warm it up much. It's well under the boiling point of water, and it sublimes. It totally skips the liquid phase, it skips the liquid phase and goes straight from solid to gas. And so because of that, I say the halogens are mostly gases. Halogens are also able to bond to themselves, so again, like hydrogen, when you find them alone in nature, it's not a fluorine, it's F2 and Cl2 and Br2 and I2 and At2. They're always bonded to themselves when they are found alone in nature. At least we think At2 will be bonded to itself. There's not enough atoms of it on Earth to know for sure. Anyway, the halogens have 7 valence electrons. It's been a while since we've been able to mention that pattern, but they have 7 valence electrons. Because of that, they only need one more to fill up their outer shell to get to the 8 that they like to have, or that shell can have, so they tend to gain 1 electron, and they end up forming 1 minus ions. Shame on me, I don't have it listed here. Halogens are also very reactive. Halogens are very reactive. So we have 2 very reactive columns. The very first column, the alkali metals, and the last column, the halogens. Anyway, one last group to color in before we start labeling other things. Our last column to color in is the very last column, and that group is the noble gases. They are the noble gases, not the Nobel gases. They have nothing to do with Alfred Nobel. And Mendeleev did not have these originally on his periodic table. None of them had been discovered yet at that point. A whole column missing. And there's a reason for that. The noble gases, also known as the inert gases, they of course are all gases. And they are inert, which is a chemistry word for non-reactive. They are absolutely non-reactive. They don't react to anything, and because of that, we never found them stuck to anything else. So most of the chemicals that we discovered, or atoms that we discovered because they are stuck to something else. So we're studying this thing, and we find that thing that comes along with it. Or we're able to find it because it was stuck to something else. The noble gases don't bond to anything, and we actually discovered helium in the sun before we discovered it here on Earth. And in fact, that's where it got its name from. Helios is a Greek or Latin word for sun. Later on, we discovered the other noble gases, and we ended up having a whole extra column be added to the periodic table. They have full valence shells. That means the outermost ring of electrons is completely filled up, which means they have 8 electrons. Of course, exception is helium. Hydrogen and helium tend to be exceptions to a lot of the rules. Helium only has 2 valence electrons, but that first ring can only hold 2 electrons, so it is full as well. Because of that, they tend to not give away electrons or gain electrons, and so they form no ions, and they have 0 charge. With that, we're done labeling the periodic table, but there are some more things, some more bits of information we should put in here. So I'm using symbols to mark them out. You can choose whatever symbol you want, but I use a diamond here for mercury and for bromine, Hg number 80 and Br number 35. Those two, they are the only 2 liquids on the periodic table. I'm using a circle for gases. Hydrogen exists as a gas. The whole noble gases column, and I cheated here and just did one big oval. It's up to you whether you circle all of them or do one big circle like I did. But all the noble gases are gases, obviously. And then if we start at bromine, the liquid nonmetal, it goes chlorine, fluorine, and then over to nitrogen, oxygen. Those elements are the only ones that are gases on the periodic table. Everything else is a solid as far as we know. And I say that because there are man-made elements. The man-made elements is questionable what state of matter they are because we've only had a few atoms of most of them. Anyway, man-made elements start at neptunium, number 93, and I used a star here for them and just used an arrow rather than drawing a whole bunch of stars. But 93 on up through the rest of the periodic table, all of those are man-made. None of them naturally occur on Earth. Also, number 43, technetium, and I don't have it on here, but number 61, promethium. Those are also both man-made elements, 43 and 61, promethium. So everything up to uranium is naturally occurring, and except for 61, promethium and 43, technetium, which means we have 90 naturally occurring elements. Also, I've mentioned already, and I don't have it listed here, but radioactive elements start at polonium and go on up. And it's polonium through uranium are radioactive, and then on up into the man-made elements. Also, the 2 man-made elements below uranium are also radioactive. There are radioactive isotopes below that, but all elements have stable isotopes underneath uranium, except for the 2 man-made ones. Also, there's a group of 3 here, iron, cobalt, and nickel. That group is known as the iron triad. We do have one thing to jot down about the iron triad. They are ferromagnetic, which means they form natural magnets and can be easily magnetized. Only those 3. Also, you could add in neodymium and a couple of the rare earth metals down in the bottom 2 rows, but They make great magnets, but the iron triad is just those three, and they're really the only three that naturally can be magnetized. Also, right off of that group, going up and down, copper, silver, and gold, those were known as the coinage metals. And the coinage metals are used to make coins and jewelry, though not as much with coins anymore. Nickel and zinc have a lot of use in coins anymore, especially U.S. coins. But the coinage metals are very, have for many years been the metals that people have sought after. One last thing, the bottom two rows here, you'll want to label them. They are known as the lanthanide series and the actinide series, or lanthanides and actinides. The lanthanides are also known as rare earth metals, although the name's somewhat a misnomer because all of them are more common than tin. They were hard to extract and they weren't very common when they were first discovered, and so it took us a while to realize that they weren't rare. But most of them are more common than tin, and tin's a fairly common metal on Earth. They are expensive because they're hard to extract, but lots of great uses of the lanthanides. The actinides underneath them are all radioactive, and most of them are man-made. But they were discovered later on. Most of them were discovered later on, at least. These groups are also known as the inner transition metals sometimes, or just the rare earth metals, both of them together. But the lanthanide series, the actinide series, are a subgroup of the transition metals.